Welcome to this video about Rudolf Julius Emanuel Clausius, a name forever etched in the history of science. Born in 1822 in Prussia and died at 66 years old on August 24, 1888, Clausius was a pioneering physicist and mathematician who revolutionized our understanding of thermodynamics. His work laid the foundation for modern science and engineering, shaping how we understand energy, heat, and entropy. He passed away on August 24, 1888, but his legacy continues to impact the scientific world today. Rudolf Clausius was born in Köslin, Prussia, in 1822. He grew up in a modest family and displayed a keen interest in mathematics and physics. After completing his early education, he studied at the University of Berlin and later earned his doctorate from the University of Halle. By the mid-19th century, he was teaching and researching topics that would redefine physics forever. Clausius' famous paper on the moving force of heat and the laws of heat, which may be deduced theorem, which published in 1850, is deal with the mechanical theory of heat, and it also shows some contradiction between Carnot's principle and the concept of conservation energy. Therefore, he started with the two laws of thermodynamics to overcome this contradiction. In his PhD thesis, he had been concerning about the refraction of light. He proposed that the blue sky that we see during the day, and various shades of red at sunrise and sunset among other phenomena, was due to the reflection and refraction of light. However, later Lord Rayleigh have been proposed that those phenomena was fact due to the scattering of light. The first law of thermodynamics, often called the law of energy conservation, states that energy cannot be created or destroyed, but can only change forms. Clausius refined this principle by showing how energy transfers occur in thermal systems. For instance, when heat is supplied to a system, it is either used to do work or increases the internal energy of the system. His mathematical formalism helped unify the concepts of heat, work, and energy into one comprehensive framework. The second law of thermodynamics is one of the most profound principles in science. It states that in any energy transfer or transformation, the total entropy, a measure of disorder, of an isolated system always increases over time. Clausius formulated this law to explain the natural direction of processes. For example, heat flows spontaneously from a hotter object to a colder one, but not the reverse. This principle underlies why certain processes, like the operation of heat engines, are inherently inefficient. Clausius famously expressed the second law in mathematical terms, introducing the concept of entropy, where represents entropy. Clausius also coined the term entropy, derived from the Greek word tropos, meaning transformation or change. He described entropy as the part of energy in a system that is unavailable to do work, emphasizing the irreversibility of natural processes. As Clausius published his groundbreaking work, he encountered stiff competition from other brilliant scientists of his era. Among his rivals were William Thomson, later known as Lord Kelvin, William Rankine, and Hermann von Helmholtz. Lord Kelvin, a prominent physicist, developed his own formulations of thermodynamic principles, including the absolute temperature scale and the Carnot cycle. While Clausius and Kelvin agreed on many ideas, they often clashed over interpretations, particularly the second law of thermodynamics and the nature of entropy. William Rankine, another thermodynamic pioneer, introduced his theories on energy conservation and heat transfer. His approach differed from Clausius, and both scientists competed for recognition in refining the first law of thermodynamics. Hermann von Helmholtz, a German contemporary, also explored the conservation of energy and its implications. While Clausius and Helmholtz respected each other, their overlapping work occasionally led to disputes over credit for key discoveries, such as the concept of mechanical energy equivalence. The principles Clausius established extend far beyond the classroom. His work is the backbone of modern engineering, particularly in the design and optimization of heat engines, refrigerators, and power plants. The first law helps engineers calculate energy efficiency, while the second law explains why no engine can be 100% efficient. Some energy is always lost as waste heat. Rudolf Clausius's contributions have earned him a place among the greatest scientists in history. His pioneering work on thermodynamics has influenced fields as diverse as chemistry, cosmology, and information theory. Clausius's term entropy even finds applications in modern computing, where it helps describe data compression and information loss. In recognition of his achievements, Clausius was awarded numerous honors, including membership in prestigious academies and societies. Today, his work continues to inspire scientists and engineers around the world. Rudolf Clausius was more than a scientist. He was a visionary who helped shape our understanding of the universe. From the principles of energy conservation to the mysteries of entropy, his work continues to influence how we harness energy and innovate for the future. Let us remember Clausius not only for his scientific achievements, but also for his enduring impact on the world we live in today.